All right, I'm gonna try to get this proof done before a bunch of people bother me and come into my room. All right, so we can see on this diagram here, we have a varying strength of magnetic field in that space due to the current in that wire. To find the strength of the magnetic field at any point in this space, you have to use Ampere's law. And that's going to be B is equal to mu naught. The I is the current through the wire over 2 pi r. Okay. And we are looking for, the first question is the EMF, where the EMF is equal to d phi dt, so the change in flux over time. What's happening is that this is moving, increasing the area in which the flux is going through. Since the flux is increasing, the current will be generated so that it creates field into the page, causing a clockwise current. So the current through this bar will end up going up. All right. Now, what we have to think about here is as we move farther away from this wire, we are going to have sections of that area, so that's going to be a dA, and it's going to have a thickness of dr, and it'll have a length of x, and as this bar moves, we'll get dx. All right, so it'll increase by the rate at which the bar is moving. And at each of these locations, the magnetic field is different for each dA, right? So what we're going to have to do is add up all the dAs in that space out to length L. All right, so let me shrink this down. Get rid of that. All right, let's see. All right, so we want E. That's going to equal d phi dt. The phi is going to be B times A. That's all dt. Now our magnetic field is going to be that. So mu naught I 2 pi r. And our A, so from one of these little spaces here, the area of that little rectangle is going to be x dr. So x distance from here to here, x times dr. All right, so again, just plugged in for B, plugged in the area. All right. So since the magnetic field changes as a function of the distance away, we're going to group the magnetic field and the dr. Okay. And this is kind of like the total L there. So we're going to add up the magnetic field over the total length L. All right, and then we end up with, so we're basically taking these two things out of the derivatives. So it's going to end up just being, so we're going to take this and this out of these parentheses and just be left with dx dt. All right. So we have mu naught I over 2 pi 1 over r dr times dx dt. That's going to be equal to that. Right? Now we have to integrate that between a and a plus L, because so if the wire is here, the first closest edge is a distance a away, and the last one's a plus L away from the wire. Okay, so we're looking at the strength of the field at a plus L away, and the strength of the field here, and kind of averaging them all up. All right, so when we integrate this, we have mu naught I over 2 pi, the ln of r evaluated in between a and L plus a, and then we still have the dx dt, which is going to end up being v. So I'm just going to put that v in that part of the equation there, and this is still equaling the v. Okay, so all of this integral right here becomes everything that's written in white. This was left, that becomes v, that goes there. All right, so next step. Won't let me shrink them. There we go. All right, finish that up. So we have mu naught I times v over 2 pi ln of a plus L over L. And that is equal to the EMF. And that should give you the first answer for part A. All right. Now there is one more part to that problem, and I think it's the one with the force. Okay, so it's the force needed to make that move at a constant speed. Let me kind of talk about that one real fast. All right, so we're looking at this again. All right, so we have a current that is moving up this bar this way due to the induced EMF. Now, if the current is moving upward, but the field is coming out of the page, we're going to get a magnetic force that is pointing this way, right? So that'll be FB. There must be a force pushing it this way, like a force applied, that has to equal FB in order for it to move at a constant speed, all right? Now, what also is happening is because the force is equal to I L cross B, the little lengths, so they're not really the whole length here, because each little DL here, it's supposed to be DL, whatever, forget about that, each little section is going to have a different amount of force on it. So the closer it is to the wire, the stronger the magnetic field is. The current is the same everywhere throughout the wire. So, I'm sorry, the little DLs will all be the same. The strength of the field is going to be different. So the closer we are to this wire, the less the force is going to be. All right, so we're going to get all these varying amounts of force along the wire. We're going to figure out what the net force is going to be. It has to match up with that magnetic, the total magnetic force there. So we are going to use that IL cross B thing. However, so ILB, we have this together. All right, we already have that. We solved for I in a previous part of the question, but when we're trying to figure out the force, we have LB already together from when we did the flux. I shouldn't have deleted that part, but that was where we had B times A, and then the B, the little bit of magnetic field times the X times the dr, right? So this dr is really the entire L, because we took this in terms of the total length. Okay, so we took the strength of the magnetic field at any point, all right, and multiply it by another distance away, which this whole value went from A to A plus L. Let me move some of this. All right, so in the F equals ILB, which we already have, we already solved for LB, which is going to be this current. Let me use a different symbol there. This is going to be capital I, which will be that current. And then we had the mu naught I over 2 pi times the ln of L plus A over A, okay? And that is the magnetic field times the length. So you just multiply that by the I, and that'll tell you what the amount of force is. All right, so again, that L is already put into this part of that equation. All right, I think you should be able to get the rest of the parts of that problem without much issue.